So let's start our journey by looking at the Taylor series. So the Taylor series is a method of approximating a complicated function using a series of simple functions. So what do we mean by a complicated function and a simple function, and what's a series, and why we bother doing any of this in the first place? Well, let's imagine you had a calculator and you wanted to work out, say, the sine of 90 degrees. So I've got the sine wave drawn out here, and 90 degrees is approximately here, so the sine of 90 should give you a value of 1. Now let's say you wanted to do that, but you wanted to do it accurate to, say, 12 decimal places. So that would mean that you could have between the numbers 0 and 1, you could have 10 to the 12 possible values that they put in, and you could have 10 to the 12 possible values that you would get out. So this means that we would have a lookup table, and this is what I mean by a complicated function. I mean a function that has to be represented as a lookup table. So for example, you would be putting in a 12-digit value for an angle, and you would get a 12-digit value for the answer coming out. And those answers would have to sit in a memory location. So let's say, for example, this axis here was actually in radians, because that's what we would tend to be using. It would mean at this point here, which is halfway along the sine curve, would that be equal to 3.14 radians? So you could say that you would need, in this instance here, 3.14 times 10 to the 12 numbers to represent all of the possible values of the outputs. So that means that you would need approximately 3 times 10 to the 12 memory locations to represent all the outputs, so you would need 3 gig of memory. Now that's clearly not what happens, because calculators were available in the 1970s and they didn't have 3 gig of memory, so there's something else going on in the background here. Now what's going on is that we're not using the system of a lookup table. What we're doing is we're approximating the function using a series of simpler functions. So what do I mean by simple functions? Well, by simple functions I mean functions that they're at their heart have only simple arithmetic operations. So for example, plus, minus, division and multiplication, squares and square roots, because these simple arithmetic manipulations can be done on a computer, or in this case a calculator. So we can come up with an algorithm, and then we can code this algorithm into a calculator, and we can use this algorithm to give us an approximation to the sine function, and this is what happens inside a calculator. Now they don't necessarily use the Taylor series for this, but they could if they wanted to. So this goes on. Next question that we're going to ask is, what functions do we use to approximate it? So what are the simple functions? Well, in this case here, in the Taylor series, the simple functions are polynomial functions. Now, don't get too worried if you're not following some of this, or some of the maths initially looks difficult. We're going to look at it in an online graphical calculator, and we'll get a graphical approach to it, so you'll be able to see it actually working here in front of you, and it becomes a lot more apparent what's happening. But let's get through and we'll get some of the maths done first. So what we're going to do is we're going to take a function f of x, which in this case is the sine function, and we want to approximate it by another function. Let's say call our function g of x. But our function g of x is made up of a sum, and that's the sum there, of polynomial functions. So that's the polynomial functions there, an x to the n. So if we were to expand this out, the summation out, we would have a0 plus a1x plus a2x squared plus a3x cubed plus blah blah blah, all the way up to an x to the n. So our central contention here is that I can approximate this sine function by adding up these other functions here. Now we know what x is in x squared and x cubed and x to the n, because they're defined functions, but we don't know what the values of a0, a1, a2, so we don't know what the coefficients are. We need to find a method of finding those coefficients. But first of all, before we get into that, let's go and have a look at it in the online graphical calculator. So this is a graphical calculator here. It's called Desmos. It's freely available online. I'll leave the link down below in the resources section. I'll also leave this file so that you can use it and have a play with it. And I do suggest you go and download this file and give it a go, because you'll really learn a lot just by messing about with it. So what are these basis functions? So let's have a wee look. I've actually drawn them out here. So there are a0 or a1x, a2x squared, a3x cubed to the 4 all the way up down, and I actually do it all the way down to x to the power of 9. So let's have a look at just each of them individually. So if I put in a0, now you won't see it at the moment because the actual constants here are just sitting in this other file here. So this is our a0 here. When I click on it, you can see that I can adjust the value for a0, and you can see that a0 is just simply a number. So for example, there it is -2, or that's it, +2. Now that's the first approximation we're going to make. So let's imagine that we're actually approximating a sine function. So how do we put in the sine? We'll simply draw the sine function and you say y equals sine x. So this has got our sine function, and our contention is that this red function here, which is a constant, is our first approximation. Well, it is actually a good approximation at this point here, and this point, and this point. So where the crossovers are, it's a perfect approximation, but it's not very good at approximating it anywhere else along that curve. So what we can do is we can start looking at the other functions and seeing how they can possibly help. So let's say if we were to take this back off again, set that back to 0, and we were to then go and have a look at the value for our a1. So there we would have our value for a1, and you can see that a1x is simply a line passing through the origin, because all it is if you remember from high school, you might have a equation of a line y equals mx plus c. Well, in this case the m is just a constant, a1, so we just got y equals a1, and the plus c would be this term here if we were to turn this on, and we would just have a y equals mx plus c, which is just a line. Okay, so that would be our first approximation here with a constant. That would be our second approximation. But of course, if we were to set that back to 0, then we can do it by eye. We could circuit by eye. We could say, well, that there is sitting at 0, and this one here would sit at, say, this point here. So you can see that our approximation is that little bit better, because it approximates it all the way along this line, but it starts going off at these points at the end here, and this point here, and there's very bad approximation obviously the further you go along this direction and this direction. So then you say, well, what we can do is we can say that we've picked a constant term here, we've also picked the gradient at that point there, but then what we could do is we could pick a rate of change of that gradient, okay, and hopefully that would hug the curve a little bit better. So that's what the third term is. So we'll go in and we'll stick in the third term here. So the third term here would be our value a2, and then you can see that we've got another curve. Now of course we're going to be adding all of these different curves up, and we're going to have to try and work out what all the values are for our a0, a1 all the way up to a9. That allows us to approximate this sine function. Now all we're doing at the moment is we're just taking guesses at them. So let's put them back to 0 for the moment. And again, I suggest you download this and give this a go yourself. It'll become a lot more apparent of what you're doing. Now let's have a look in this folder here. And this folder here has got the final series. Now the final series here is going to be our a0 plus our a1x plus a2x squared, a3x cubed, a4x to the 4, so on and so forth. Okay, so that's this function here that we're going to draw out. So let's look at the values for all our constants and let's see if we can approximate. So that's the first value there, as we've seen before. That's the second one, which is the line. The third one, it starts to curve. The fourth one, it curves in a certain different direction. Okay, and then you can continue on like this, so on and so forth. But of course, there's nothing systematic in the way I'm doing this, or nothing mathematical. I'm just simply messing about with the constants to see if I can try and create that sine function. And of course, I'm failing quite miserably. Okay, but the contention then is that we can create this sine wave if we can just find the values for A0, A1, A2, A3. If we can pick out the right values for those constants, then we'll be able to approximate that sine wave. So now we've seen this, let's go back to the mathematics and we'll see if we can derive a method of finding the values for our constants. So we're looking to find these constant terms A0, A1, A2, A3, all the way up to AN. Now we've seen from the graphical calculator that if we had a function here, we'll just call this function in blue y equals f of x. So that's a function we want to approximate it. And we're going to approximate it by adding up these yellow functions here. So our intuition tells us that what we can do is we can look at a value of x0. So x0 is the value at the origin. And we can say, well, let's look at the value of f of x at the origin, which is just that height there. And we'll let that be the height of the function that we're looking to use as approximation. So in that case there is just the height a0. So the yellow one there just crosses the axis there at the same point as the blue one. So that's a good approximation, but it's a good approximation only at that one point. When we move further out here, the approximation becomes worse and worse. So we then said that what we could do is we could look at the gradient of this function here at that point, and we could ensure that the gradient of the approximating function is the same at that point. In that case there, it would just give you this line here. So the first one here, we're just saying that a0, so that's the approximating function, it just equals the value of the function f at x0. And the second one here, we can say that a0 plus a1x, that's the approximating function, is going to equal to the value of the function f at x0, and this value here a1 will simply be the rate of change of the function f at x0. So don't get confused about this. All we really have here, if you remember back to some basic high school maths, the equation of a straight line is y equals mx plus c. So this value here, a0, would be the plus c bit, and the m would be the gradient there, a1. And the right hand side here, that would just be the value there, a0, and the gradient just given by the derivative of the function f derivative at x0. Now our contention was that if we continue doing this and we make sure that the third derivative of the function f of x is equal to the third derivative of our approximating function g of x, and the fourth derivative equals a fourth derivative, and so on and so forth, then we should have a good approximation to that function. But don't forget, at this point here, it's purely intuition. There's nothing here that tells us that we actually will have a good approximation, but it seems that that may well be the case. So still we're left with the problem of finding these coefficients, but we've actually got a solution for it here, because what we want to do is we want to make sure that the value of the function g at x0 equals the value of the function f at x0. The value of the function, the first derived of the function g at x0, is equal to the first derived of the function f at x0, again with the second, third and fourth. So let's just write down what the function g of x is. Well, g of x is a0 plus a1x plus a2x squared, so on and so forth. So when we differentiate it once, we get this here. so the constant term disappears. We differentiate it twice. Now that constant term there disappears. We differentiate the third time. This constant here disappears. And we differentiate the fourth time. This constant disappeared. So you can see then that we're going to end up with this function here at the bottom. But remember now, we're doing it at the point whenever x equals 0. So all along here you can put the value of 0 in for each of these. So all you're going to be left with is gx0 is going to equal, well, it's going to be equal to a0, and we know that from above here. So that's a good start. G of x0 equals a0, which is the f of x0. We differentiate once, and we can say the g derived of x0 is equal to, well, all these other terms disappear because they've got an x in them. We're just going to be left with a1. So g1 at x0 is just equal to a1, which is f1x0. So that's f1 just means the first derivative. So again, that's excellent as well. It means that the value of the function is equal, what we'll use as the approximation, is equal to the actual function at that point. The first derivative of the function is equal to the first derivative of the function f at that point as well. But it starts to fall apart a bit when you go on to the second derivative, because now we've got not a value of a2, we've got a value of 2a2, and then a value of 6a3, and a value of 24a4. But we don't want to have these terms, the 2, the 6 and 24. We just would rather have it as a0, a1, a2, a3 and a4. So they're out by a certain factor, but we can deal with that, quite simply. So we can see that we wanted the nth derivative of the function gx0 to equal the nth derivative of the function f at x0, but it doesn't quite equal it. It's out by these factors of, in this case, 2, 6 and 24. So it's actually out by a factor of n factorial. So you can see that in this instance here, if you took the value 24, then the n factorial is going to simply be the 4 factorial. So n is 4, so 4 factorial is 24, 3 factorial is 6, 2 factorial is 2, and 1 factorial is just 1. In this case here would be 0 factorial, which is defined as being 1 as well. So we've got this factor of n factorial, so all we need to do in order to make it all right is divide throughout by that factor of n factorial. So that means that we can say that the value for our an is simply going to equal the nth derivative of x0 upon n factorial. So that means that we can take this an here and we can put it back in for our function g of x. So it means that our function at g at x0 is just going to be equal the sum from n equals 0 to, and that should be an I, of the value of our an times our x to the n. Well, we know our value of an, our value of an is just this simple value here. So that's going to be the nth derivative of the function at x0 all upon n factorial times x to the n. So now finally we know that there's going to be an approximation, so we're going to have to add in an error. So we're just adding in the extra term epsilon. Okay, so that means that we can say that our g of x is going to equal the sum from n equals 0 to some value of I of the nth derivative of our function at x0 all upon n factorial plus x to the n plus the value of epsilon. So that there is how we're going to produce all of our Taylor polynomials. Now, what we've seen previously was actually called the Maclaurin series. So the Taylor series centred at the origin is called Maclaurin series. If it's not centred at the origin and it's centred at some other point, x, then we can simply deal with that by saying that g of x is equal the sum from n equals 0 to I of the nth derivative of x0 over n factorial at the point x minus x0 to the power of n plus epsilon. So that just allows us to extend the idea of our Mcgowan series to any point on the x-axis. So there's a bit of maths involved in that, but if you sit back and read through it, mess about with the graphical calculator, and I'm sure you'll be able to convince yourself of it. Now, the thing that's interesting here is that we have a method of finding this approximation, but it doesn't really tell us whether it's actually going to be a good approximation or not. We would have to look at the error term and work out the error term, and from that we can see how good our approximation is. Now, this isn't a maths course, we're not going to get into that detail, but that's something that's quite interesting and useful, and it's worthwhile to go and have a look at yourself. So it's best seen by example. So let's have a look at the approximation to the sine function using the Taylor series. And this is us going back to the problem we had in our graphical calculator. We were messing about with the values A0, A1 all the way up to A9 and trying to do it by hand and eye to try and work out what those values are. But now we've got a method of finding those values. So let's work through that method of finding the values. We'll get those values and then we'll take them and we'll put them back into the graphical calculator and just by eye we'll see how good the approximation is. So we can see then that we're interested in the function f of x. So function f of x is sine x. So if we differentiate it once, we get cos x. Differentiate it twice, we get minus sine x. Then we get minus cos x. And we differentiate that, we'll get back to sine x. And the process would then repeat as cos x minus sine x minus cos x to sine x and so on. But we're looking for the value of the function at x equals 0. So we're looking at the value of the function f at x equals 0. Well, sine of 0 is simply equal to 0. The cos of 0 is equal to 1. The value minus sine x is equal to 0. And minus cos x is minus 1. And sine x is equal to 0. So it means that the first term there is going to be 0. The second term is just going to be 1 upon x to the power of 1 upon 1 factorial. The next term will be 0. Next term will be minus x to the 3 upon 3 factorial. And the next term here will be 0. So we can see the pattern that's going to occur here. We're able to say then that sine x is going to be equal to x minus x upon 3 x to the 3 upon 3 factorial plus x to the 5 upon 5 factorial minus x to the 7 upon 7 factorial plus x to the 9 upon 9 factorial, so on and so forth. So our contention here is that the numbers that we've been looking for are 0 and a value of 1, a value of minus 1 upon 6 plus 1 upon 120 minus 1 upon 7 factorial plus 1 upon 9 factorial. So those are the numbers that we're looking for. So let's go and we'll put these numbers back into the graphical calculator and see what the approximation is going to look like. So let's start putting our values in for our constant terms here. So we've seen from the Taylor series expansion for sine x that the first term a0 is going to be 0. The second term a1 will equal to 1. So that's our first start on our approximation. The second term here, that term a2, is equal to 0. The third term is equal to, in this case it's minus 1 upon 6. Okay, so that's 1 upon 3 factorial. So that's our second approximation there. You can see it hugging the sine function quite well. So our a4 again, that's going to be 0, and our a5 is going to be our, so that's going to be 5 factorial. So 5 factorial is 120, so it's going to be 1 divided by 120, and you can see that next approximation there appearing. The next value is going to equal to 0, and the next value is going to be equal to minus 1 upon 7 factorial. The 7 factorial is 5040, and then you can see the approximation. And then the 8th one is 0, and then the 9th one is going to be equal to 1 upon 9 factorial. The 9 factorial is actually 362880, and there you see our approximation there now. So you can see then that our approximation works quite well up to round about 4, and this is in radians, and -4. Now if we keep adding in more and more approximations, then the approximation of the sine function becomes greater and greater, more accurate the further along the away from the origin that we go. So you can see that this does work, and it's working quite well. And that's really all I have to say about the Taylor series. I think that it's worthwhile downloading this tool and giving it a little go, and you can play about it yourself, and it'll give you a good intuition. So thank you for listening, and I'll get you on the next video. Goodbye.